Our goal in this last video will be to just kind of wrap up some of the ideas behind a radical function as it pertains to some additional applications or pretty cool stuff that we could run into. So in any situation where there is any situation that can be modeled by a quadratic can also really be, in most cases, in a lot of cases, be modeled by in some way by a square root function. Took me a little while to think of that. So polynomials, so a quadratic is called a polynomial because remember it has that form, something x to a whole number power plus something x to a whole number power plus a constant. And so that polynomial is a sum of terms, or maybe one term, two term, three terms, etc., that have the variable raised to a whole number non-negative power. And a square root is basically just the opposite of that, right? In other words, squaring and square rooting are sort of opposite actions, and so these two are often called inverse functions. Anyway, so some of the common places where we run into square root functions, you might be wondering, well, how do you even form one of these? How do you know when to form a square root function? Well, most of the time, there are functions out there like in physics and different sciences where there's a square root because of maybe the original model was in some way quadratic. For example, let's say that we're talking about carpentry, and in carpentry we're dealing with right angles, and so right angles, let's say that maybe we're talking about forming the pitch of a roof. So maybe this is going to be a roof, so I guess I kind of have it upside down, and depending on what this angle needs to be, maybe this angle here needs to be 90 degrees for some reason. Well, to determine other sides, so maybe you know how long the house is, and you need to determine, maybe how long this side is going to be, and so anyway, you need to maybe determine other components, or how do lengths vary whenever you change two of them. So we know that, for example, if we call this side, so let's pretend like we've kind of rotated this roof to kind of look at it as a triangle, and so good old Pythagoras had a nice little theorem that told us that the square of A plus the square of B equals the square of C. So this has to do with side length. So if I know that this side is A units long, this side is B units long, and this side is C units long, then I can form this relationship here. So a really important thing when we're dealing with specifically right-angled or right triangles, we call this a right triangle, and this extends to many interesting applications, but I just kind of want to show you how we would form one. Well, let's say that our goal is to really understand maybe this side right here. Maybe we'll call this side, I guess this side would technically be A, right? If it were rotated, this would be B and this would be C. And we really want to understand, maybe for whatever reason we know how long C is because we know that the house is going to be a certain length, and we know maybe how long this needs to be because of the way of the pitch is going to occur. And so I can write this relationship. So really what I'm interested in determining is, how do I figure out what A should be based on those other dimensions? Well, you've probably done this before, where now you can say, well, if I knew the values, I could plug them in, and then I could solve for the unknown. Okay, well, this is not a simple equation in terms of solving, but if let's say I knew what B and C were, and I wanted to solve for A. So what could I do? Well, if I know that the sum of this and this equals this, then that means that this, A squared, must be the difference between C squared and B squared. And, okay, well now I want to solve for A. I don't want to know what A squared is. I want to know what A is. So, well, what's the opposite? How do I take action to be able to undo a square? Well, square and square root are opposite actions, right? Just like addition and subtraction are opposite actions. And so if I took the square root, right, because as long as I square root both sides of the equation, I'm essentially keeping it balanced. And so now I'm able to say that A, because again, let's think about this. If I have 3 squared is 9, and the square root of 9 is 3. So really, we can kind of think about those as canceling each other out. And similarly, the opposite goes as well. If I take 9 and I square root it, and I want to get rid of the square root, well, if I square root 9, I get 3, but if I square that result, then I'm going to get 9 back again. So regardless of whether I square root a square or I square a square root, they're opposite actions. It's kind of like saying if I have 3 and I subtract 3 versus if I have negative 3 and I add 3, then those both kind of cancel each other out, right? They zero each other out. So I'm left with a equals the square root of c squared minus b squared. And most of the time we've got to put the plus or minus here because technically a could be a positive value because when you square it you get a positive, and it could be a negative because when you square it you get a positive. But here's what it boils down to, and we know we can't reduce this anymore because the square root of, in this case this is I guess a sum, c squared plus negative b squared. I can't just take the square root of each one individually, but I'm able to form a function. So maybe I always know what c is going to be. So let's just say that I know that the house is going to be maybe, I don't know, maybe this is going to be, maybe this is too long or too short, I can't really think. Let's say this is 50 feet long, so I guess kind of a long house. And now I know that c, right, the roof, maybe the roof has to extend 6 inches on either side, so maybe I know that the roof, the dimension of c is going to be 51 feet. Okay, so then I have a equals the square root of 51 squared minus b squared. Alright, well I could certainly figure out what that is. And I'm going to come up with 51 squared equals 2601. So now my equation becomes a is equal to the square root of 2601 minus b squared. Very cool. So now I'm able to talk about the relationship between a and b. And maybe you want to call them x and y. I don't know. Some people prefer that. So maybe I'll treat the b as the x and the a as the y. So that really gives me y equals the square root of 2601 minus b squared, x squared. So x is really this dimension, and a is going to be this guy over here. So now I can kind of begin to understand, well, what happens as I increase b or change the value of b? So I'm going to plug this in, the square root of 2601 minus x squared. And now I've got to think about, okay, well, what should my window setting look like? Well, because I'm taking 2601 minus x squared, 2601 minus x squared, the first question I want to ask myself is, when is this quantity 0? And we know from the past videos that if we can figure out when the square root is 0, then I know that if I make x smaller than that value or x bigger than that value, I'm either going to make the quantity under the square root negative or positive. So this 0 point is important. So when is this thing equal to 0? Well, I could use the quadratic formula here if I wanted to, but since I don't have a bx term, check this out, I could actually move the x squared over and write 2601 equals x squared. And now I know that this is basically just telling me that some quantity, let me write this the other way around, x squared equals 2601, that some number squared gives me 2601. Well, what number must I multiply by itself to get 2601? Oh, gee, that sounds an awful lot like a square root of 2601. So I know I can't, if I'm dealing with lengths, it can't be negative. So the square root of 2601, the square root of 2601 is going to be 51. Oh, well, I guess we knew that, right? We had to square 51 in the beginning to get 2601. So I know, well, what does that tell me? That tells me that this function is going to have, that y is going to be 0 when b is equal to 2601. Well, what's the significance of that? The significance of that is that if I make x bigger than 2601, then, so let's try this. If I make x bigger than 2601, then I'm going to get x squared being, sorry, if I make x bigger than 51, then this guy is going to be bigger than 2601. And if x squared is bigger than 2601, then I'm going to get 2601 minus a bigger number is going to be a negative quantity, and the square root of negative quantity is undefined. So essentially, I can make x smaller than 51. X can be smaller than 51, but x cannot, and I'll just strike this out, x cannot be bigger than 51. Otherwise, I'm basically saying that my roof, that this side is longer than the base, and there's no way I could form a right angle at that point, right? Because beyond a certain length, now there's no way I can form a right angle up here. So let's see if we can set our window correctly. So we basically want to look at, well, x probably can't be 0, but I'm going to go ahead and start it at 0 and go up to 50. I'm going to go up to 50, 60, just for the sake of showing us that beyond 60, this function is going to be undefined. And let me just go from, I don't know what these heights are going to be. I guess I could kind of use my table to help me figure this out. If I start my x dimension at 0 and go up by increments of 5 feet, then there's kind of my table value. So it looks like the biggest I can have is around 51, and it seems to decrease from there. So, see, and then right there we're getting errors already, because if x is bigger than 51, we start to get a negative under the square root. So I'm going to go up to maybe from 0 to 50 on my y, because it seems like, or 0 to 51. And there it is. So what am I looking at here? Well, I'm looking at y, I'm measuring y, which is this side of the roof, as a function of what length I make this side. So what's happening here? Well, as I increase the value of x, this side, then I'm needing to decrease the value of y, this side. Why is that the case? Well, if I make this side longer, then this side is only going to need to be shorter in order to still form that right angle. In other words, the farther I go out here, or I guess, excuse me, not even so much at this particular angle, but in order to form that 90 degrees, I'm going to have to basically decrease the pitch of my roof. And if I decrease the pitch of my roof even more, then the length of this side to form the 90 degree here is going to get smaller and smaller. So I guess I kind of misrepresented that drawing, but so here's the length of my, there's my house, and so if I make the roof really short, then I'm going to need to make this side really long in order to still have that 90 degree angle right there. But if I make this side really long, excuse me, let me make the angle might change depending on the length. If I make this really long, then I'm going to need to make this really short in order to still form that 90 degree angle. So that's kind of the reason we're noticing that, and why we're seeing this kind of behavior. Well, that's just based on the relationship of Pythagorean theorem, that the more I increase, for every additional increase in x, y, this dimension, actually drops very rapidly, right? So here initially, when I increase this length by 1 unit, y doesn't drop too much. That is, this length doesn't change too much. But as I begin to go out here, I don't know, what is this, from 31 to 32 feet, y drops by a lot. From 31 to 32 feet, the length of this guy drops quite a bit. And that's because of Pythagorean theorem. So anyway, this is kind of a really interesting example to look at. Anytime you're also dealing with cubics, like for example, and this is kind of maybe more of a cliche example, but let's say you're dealing with some sort of volume of a container, and let's just say this container is perfectly cubic. If this container is perfectly cubic, and so all of these sides are of the same length, and let me just call this side of length s, so this guy has a length of s, this guy has a height of s, and we have a width of s as well. Well, the volume would be s times s times s, area, or length times width times height, which is the same thing as s to the third power. Well, okay, well now maybe I want to figure out what's happening, what do I have to do with my sides if my goal is to be able to set my volume. Like let's say I want a specific volume. Well, certainly I could plug it in, plug that volume in, and then take the cube root of both sides. But sometimes the goal is to say, let me get a function that tells me my side based on what my volume is. So in order to undo a cube, or the opposite of a cube is a cube root. Just like the opposite of a square is a square root. And so that sort of, I guess, cancels these out, and I'm left with the cube root of the volume will give me the required side length. So let's take a look at this guy. If I take and how do I do a cube root in here? Well, there are two ways. A square root is something to the 1/2 power, so a cube root would be something to the 1/3 power. Alternatively, I could actually go grab the cube root symbol, and to do that I would go over to math, And there it is. Option 4 would be the cube root of, and I'm going to use x to represent volume. And now I can kind of take a look at, let me look at my table. So let's say I wanted a volume of, a volume of 40 cubic feet. So if I wanted a volume of 40 cubic feet, I would require each of my sides to be about 3.4 feet long. If I wanted a volume of, let's say, 100 feet, then I would need each of my sides to be 4.6 feet long in order to form a perfect cube. And this also extends to any volume. So let's say you're talking about the volume of some sort of cylindrical figure. Well, the volume of a cylinder, if this is the height, and this is has a radius, so the radius is, r units long. Well, the volume of this type of figure would be, well, this is a circle, so it's the area of a circle, which is pi r squared, and then it's a bunch of circles, 8 circles sort of stacked on top of each other, so pi r squared height. And in this case, let's say I wanted to figure out, if I knew my height, and I wanted to figure out, I knew my height and I knew my volume, but I needed to know my radius. Well, I could solve for the radius, so I divide both sides by pi to get rid of that. So I have v over pi equals r squared times height. And now I want to isolate r squared, so I could also divide by the height, or I could have done it in the same step. I could have just divided by pi h and canceled both of those out. And so now I have r squared equals v over pi times h. And now to get rid of the square, I would square root. So the required radius for volume v and height h would be this following formula. So now I've got something that involves a square root, and it involves the volume. So let's just say I wanted a volume of, I don't know, maybe 100 cubic feet, and I needed that, and this could pertain to something like a concrete pillar in a building. You want to talk about, okay, how much concrete is that pillar going to take, or maybe what should the radius of that pillar take? Maybe I need to use up 100 cubic feet of concrete, and let's just say my height, is going to be, maybe I need that to be 10 feet high. Well, now I can figure out what should be the radius of that pillar. So the radius of that pillar would be the square root of 100 divided by pi times 10. If I could do this in my calculator, I could actually take the square root of 100 divided by, I'm just going to put 10 pi in parentheses just to make sure that the graphing calculator knows that I should divide by 100 by 10 pi and not divide 100 by 10 and then multiply by pi. So this would tell me that I would need that pillar radius to be 1.78 feet. So this would need to be, here's my pillar. I'm sorry, you can tell I'm an expert at drawing these. That if I wanted this to be 10 feet tall, and I wanted this to contain 100 cubic feet of concrete, then the radius of this pillar would need to be 1.7 feet. So hopefully that helps to kind of give you a little bit of context as to how these things actually come about, because I know it's somewhat cryptic, like when would you know to have a when would you know to have a square root function? It's a little bit more obvious for a linear and a quadratic, and maybe even an exponential, but for a radical and rational functions, they're not as obvious, and so I think it's important to kind of see some of the neat applications that we can have.